This is problem number 6 from the 2011 AP Calc AB free response set. And the setup here is basically just that they give us this piecewise function. So as long as x is less than or equal to 0, the function is defined to be this. And if x is greater than 0, the function is defined to be this exponential. What we're asked to do in part A is to show that f is continuous at x equals 0. So graphically, what we've said a handful of times, that in order to consider a function continuous, you can't have a hole, you can't have a jump, you can't have an asymptote in a given location and still have it be continuous there. So we need to make sure none of those things are happening at 0. And the main thing that we're going to have to worry about is a jump. Do we jump from one location when the first piece of the function ends to another location when the next piece of the function picks up? Using the definition of continuity, this boils down to 3 things all happening. F of the value you're considering, and in this case it's 0, must exist. And so, well, when x is equal to 0, we're defined to be this top piece of the function, and if you evaluate that, you get 1. So f of 0 definitely does exist, so check mark there. The limit as you approach 0, the same value you're considering here, also has to exist. And so here I immediately broke into one-sided limits because I realized on the smaller side of 0, x's that are less than 0, I'm going to be approaching on this piece of the graph, and then for x's that are bigger than 0, I'm going to be approaching on this piece of the graph. So on the bigger side of 0, I use the bottom definition for the function, and then to evaluate that, I just tossed 0 in place of the x, and I got e to the 0, which turned out to be 1. And then as you approach 0 from the smaller side, we're using the top definition here. And if you evaluate that at 0, you get 1. So since these two one-sided limits equal each other, this overall limit is also going to be equal to that same thing. So check mark, yes, this does exist. And then the last thing that has to happen in order for a function to be continuous at a given location, these two pieces must be equal to each other. So the limit as you approach the value you're considering must be equal to the function value at that x. And we got 1 for the function value, we got 1 for the limit value. So yes, the limit and the function value are equal to each other, third check mark. We're definitely continuous at 0. In part B, they want us to find the derivative as a piecewise function, so I just left the intervals here alone, and I just took the derivative of each component, and the derivative of the top component ends up being this, and then the derivative of the bottom component, using the chain rule, ends up being this. And then I wanted to figure out when this derivative was going to be equal to -3. So I wanted to first consider whether or not this could be equal to -3. So I set the top piece equal to -3, and I ended up here, when I divided each side by -2, getting cosine of x equals 3/2. Well, cosine of x is going to range between -1 and 1. I can't take the cosine of 3/2, that's undefined. So this piece is never going to be equal to -3. So we moved on to the second piece of the derivative, set that equal to -3, divide by -4, natural log of each side to get rid of the exponential, divide each side by -4. You get kind of an ugly value here, but it is an acceptable value. So when x is equal to whatever the numerical value of this is, we're going to have the slope of the tangent line, or the value of the derivative, equal to -3. And then in the last part of this, they wanted you to find the average value of this function on the interval from -1 up to 1. And so the average value of a function formula is this: 1 over the difference between the interval that you're considering times the integral of that function across the interval that you're considering. And so I just simplified this a little bit. 1 minus -1 got me a 1/2 out in front. And now it's a matter of trying to compute this. And that's going to take a considerable amount of work, because if you think about computing this integral, you're not defined by the same rule clear from -1 to 1. You have a split in how this function's defined at 0. So because of that, we had to split this integral into 2 separate halves. When I'm considering from -1 up to 0, the function is going to be defined to be this, and then when I'm considering from 0 up to 1, the function is going to be defined to be this exponential. So taking the antiderivative of this, using the first part of the fundamental theorem of calculus, gets me x for the antiderivative of 1 with respect to x, and then the antiderivative of, well, the negative 2 is going to stick around within our antiderivative. Notice I have a positive 2 here, and that's because think about the antiderivative of sine of x. It's going to be negative cosine of x. So I really had negative 2 times negative cosine of x, and that ended up being positive 2 cosine of x when you simplify the product. This integral is going to be a little bit tougher to take because you have an inner function here, so you have to let u equal that inner function. And then you have to determine what you're going to be able to replace dx with. So du dx is negative 4. Solving for dx gives us du over negative 4, which goes in place of the dx. I haven't changed my limits of integration. Those are x values, so I need to be careful to make sure I put those in place of x and not accidentally put them in place of u. Now the antiderivative of e to the u is e to the u. Since I was kind of running out of room at the bottom of the screen here, I went ahead and put negative 4x back in place of u. Here's this factor of negative 1/4 that we picked up by doing the substitution, and then we would have to evaluate this from x equals 0 to x equals 1 and take a difference. So putting 1 here, you get negative 1/4 e to the negative 4, and then you'd subtract negative 1/4, so I just added 1/4 e to the 0, and e to the 0 is 1, and that's why you don't see an exponential on this piece. And then on the other side, since we're evaluating at this point, when you evaluate this at 0, you end up with a 0 there, and then cosine plus 2 cosine of 0, and then minus, and then evaluate this at negative 1, so you get a negative 1 there, and then plus 2 cosine of negative 1. Distribute the negative in, which I guess I didn't do a very stellar job of, because I did distribute it into the negative 1 here, and I had cosine of 0 being 1, 2 plus 1 giving me 3, but then I guess this is going to have to end up being negative. So plus negative 2 cosine of x when I distribute the negative into this piece, and then plus the quantity we were already looking at. And then I had to go to another screen to finish this, and I guess I do have a sign error down through this screen. We decided this is supposed to be negative, that's supposed to be negative, that's supposed to be negative. But bring the 1/2 back into the mix, and that's, again, from the average value of a function formula. And then just kind of continue to simplify this, distribute in, and you get this very ugly answer. I have no idea what the numerical value of this is without getting a calculator to help me approximate it, but it is going to be the average value of that function that's defined on the interval from negative 1 to 1, even though it is a very ugly answer. This is the best we're going to be able to do when there's no calculator in play.